Hey everyone, welcome back to Probability Theory. This will be lecture 1 of the course. And in this section, we're going to pursue a sort of conversational, sort of leisurely introduction to probability. So we'll obviously get far more rigorous and well-defined in coming lectures, but in this section, what we want to do is just kind of introduce some ideas about probability, sort of how we think about it, and give some context for where we're headed. So let's go ahead and jump into it. And we'll call this section 1.1, Introduction to Probability. So the term probability, right? So the term probability, right? What does it mean in kind of everyday language? Well, I mean, one good way to describe what we mean when we talk about the probability of something is to say, and I'm quoting from the text here, the measure, right? The measure of one's belief in the occurrence of a future event, of a future event. So if I say the probability that such and such will happen, what I'm really saying is I'm really kind of giving you a measure of my belief in the occurrence of a future event. I'm giving you my measure of how likely I think such and such is to actually occur. Okay, and so this is kind of, I think anybody can kind of get behind this sort of basic idea about what we mean by probability. Most people would probably, if I were to ask, what do you mean? What does probability mean? Like, what's the definition? This is probably close to what many people would suggest. Okay, and so that's the starting point. Like, the starting point is like, what do we think we mean by probability? Now, it needs to be said that probability is used constantly. So we use probability constantly, right? And I can think of many examples off the top of my head. When we drive a car across a bridge that's got a lot of traffic on it, we know that it is possible for the bridge's maximum load to be exceeded, but we judge that it is highly unlikely to be exceeded, right? And so we assume we're safe to drive across, along with many others. A very common example of probability in everyday life is the probability of a baby being born, male or female. We assume an equal probability of boy or girl at birth. All right, we don't know. Well, nowadays we do know, but prior to checking, we assume that, hey, there's an equal chance of either, right? This is a very concrete example. Another example, kind of less one that you maybe hadn't thought about, is when you have a vehicle, an automobile. We know it's just a matter of time before our vehicle's mechanical components expire. We use that information we use that knowledge to judge the fitness of our vehicle for extensive travel. So cars break down, we say randomly, right? But there's some component of that is sort of well understood, like, hey, a transmission should last you 100,000 miles, or hey, these tires are good for such and such time, mostly. So cars break down randomly, but we still assume an average longevity and use that info to judge the fitness of our vehicle for lengthy travel, right? I'm not going to hop in a car that is 50 years old and on its last leg. I'm not going to hop in that car and drive to California from New York, am I? I'm not likely to. But if I go buy a brand new car off the lot, I'm highly likely to be okay with that decision, right? And it's because we assume that the cars have a certain reliability, a likelihood of breakdown, etc. Right? So it's a kind of probabilistic argument and assumption that we make. Kind of related to this is that we know that human life has an average length. I don't know what life expectancy is currently, but human life all has an average length. Let's say it's 80 years old. E.g., I don't know if that's right. Don't quote me on that. But we assume human life has an average length. Of course it does. And our own lifespan is somewhere in relation to that average. Our own lifespan is somewhere in relation to that average. Right? And this is a fact that we live with. When we're very young, we wake up in the mornings and we don't really worry or even think too much about death. As we get older and older, we know that the likelihood of today being the day increases, right? This is an example of probability, right? This is an example of probabilistic thinking. Of course, young children aren't thinking about explicitly in probabilistic terms, but the fact that they don't think about it comes from this. So these are all just kind of off the top of your head kind of examples. There's many, many more that you could come up with. The point of kind of bringing these up is just that random events such as these, they cannot be predicted with certainty, but the relative frequency of such things such as these, given lots and lots of trials, is very stable. So these are examples of random events, right? They cannot be predicted precisely, right? We don't know exactly when our car is going to break down. We don't know exactly whether we're going to have a boy or a girl. We don't know exactly how long our life is going to be, right? So they're examples of random events. They cannot be predicted precisely, but given lots and lots of trials, right? Meaning lots and lots of babies being born, lots and lots of cars breaking down and not breaking down, lots of human lives. Given lots and lots of trials, these events, they sort of settle into stable distributions. Okay, and we'll talk more specifically later what a distribution is, but we know, for example, that about 50% of babies born are male and about 50% of babies born are female. And so that's an example of a stable distribution. We know that on average, human beings maybe live 80 years, and that plus or minus that curve that would define that distribution falls off in a steady and regular sort of way. So these are examples of random events. The point being, we can't identify precisely what's going to happen, but these things, as we observe and measure them over time, we notice sort of stable patterns. Okay. And so probability theory is kind of based on this idea, right? So we can use the long-run stability of these kinds of events to provide meaningful insights, even if we can't make perfectly precise predictions. So we can use the long-run stability of such events to provide meaningful insights, even if we cannot make 100% precise predictions. Okay, right, and so that's kind of a good place to start. Let's think through some examples here. Right, so coin tossing, right? This is going to come up constantly in this class because it's just such a perfect example. When I flip a coin, I can't state with certainty that I'm going to get a tails on a specific coin toss. So I can't say with certainty that I'll get tails on a specific toss, right? I know that, right? Something I can say with certainty, though, is if I flip a coin 1,000 times, but if I flip a coin 1,000 times, I can say with certainty, and I'll say relative certainty, I'll say with certainty. I can say with certainty that the proportion of flips that land as tails will be close to 50%. Right? So even though I can't precisely tell you what the next flip is going to be, I can't tell you, hey, this flip will be tails for sure. I don't have that ability. But I know enough about how coins work and about how coin tosses work in a probabilistic sense that I can say with certainty, if I flip a coin 1,000 times, about 500 of those are going to be tails, plus or minus, a few, right? I can say that with certainty. That's the power that you get from probability theory. Okay. Now, this idea of doing something many, many, many times and observing the outcome it's sort of one avenue into probability. So doing things many times and observing the outcome is one way, so I'll say one avenue into probability. Right? This is sort of the empirical side of probability. Right? It's this idea of, hey, I can just, if I want to know the probability of something, I should just do it over and over many, 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 many times and just keep track of what happens. And from that, I can extract the probability of it happening on a single flip. If I want to know the probability of getting a tails, I can just flip a coin 1,000 times and note that about half of the times I get a tail. So that tells me that, hey, if I flip a coin, the probability of getting tails is about 50%. Okay. So this is like one avenue into probability. And this is a lot of times called the empirical probability. Right? And this is the kind of probability that we're sort of used to in our everyday thinking, right? Our everyday reasoning, we sort of think about probability in this sense, right? I have a certain assumption about how likely it is that I'm going to die today, and it's based on the fact that I didn't die yesterday, I didn't die the day before that, and all the people around me didn't die. So I have a certain sense of the likelihood of my death in any given moment. I have a certain sense that certain activities are more deadly than others, right? And how do I know that? Well, I know because I've observed that mortality rates can increase, right, when dangerous activities are being done. I've heard this anecdotally. Maybe I've even seen data on it. One thing I haven't done is work out rigorously what the probability is of these things, but I have a sense for it based on this sort of empirical probability concept. Now, another avenue into probability, and the one that we'll be focusing on early on in this course, is to define and construct the space of all possible outcomes of an event, and then to extract the probabilities from this construction. So another avenue into probability is to construct rigorously construct the space of all possible outcomes of an event and then do analysis on that sample space. Right, and so this is another way. So there's kind of like two ways to think about probability. You got this sort of empirical probability, and then this is sort of the theoretic probability. Right, and what we'll be focused on is this theoretical probability. Right, we want to understand how probability works in the small. Right, this is a math class. Right, that's first and foremost. We want to understand like exactly what's going on when I say that the probability of a tails is 50%. What does that really mean, like fundamentally? And so that's going to be our focus for this early section of the class. Now later on, we'll bring this empirical probability idea into the fore as well, and we'll see how they kind of work together. Let's take a look at another example. Right, another example that'll get a lot of play in this class is the dice rolling. Right, so rolling a die or a pair of die later, but we'll start with just one. Right, so everybody remembers what a dice looks like, or a die singular. Right, it's a six-sided, it's a cube basically, right, and the cube has a number denoted by a handful of dots on each of the faces, right? So 1, 2, 3, 4, 5, 6. So 6 sides, 6 numbers, right? So when we roll a die, there's 6 possible outcomes, right? 1, 2, 3, 4, 5, and 6, namely. Now, if we assume a perfectly balanced die, and if we roll that die, maybe we'll say 1,000,000 times, we would find that approximately 1/6 of the rolls would be 1, 1/6 of the rolls would be 2, and so on. So if we roll a fair die, right, so it is possible to weight these things and to make them less fair. If we roll a fair die 1,000,000 times, we'd expect, what would we expect? Well, we'd expect, maybe 1/6 would be 1, 1/6 would be 2, and so on, right? Right, that's what we would expect if we were to do this. And so we can kind of visualize these potential outcomes using what's called a histogram. Right, so a histogram, let's draw a histogram for this. Histograms are also sometimes called bar charts, right? But a histogram basically is a kind of chart, right? We'll have two axes. On the y-axis, we'll have the count, how frequently something happens, and then on the x-axis, in this case, we'll have the number on the face of the dice. So the events, the outcomes. So we'll say the number showing on the die, right? So of course we know that you can have a 1, a 2, a 3, a 4, a 5, or a 6. Okay, and what we'd find out if we were to do this, and maybe we do it 1,000,000 times, what we'd find out is that pretty much each number would be equally represented, right, in this histogram, meaning there would be roughly, I think, if you divide 1,000,000 by 6, you get 166,666, right? So there'd be roughly 166,666 ones and roughly 166,666 twos, right? And so this is an example of a histogram, or we would call it a frequency distribution. This is an example of how to visualize it. Okay, so this is the assumed distribution of die rolls whenever one is rolled, right? So if I'm going to roll a die, I before I roll it, I don't know what it's going to be, but I assume it's equally likely to be any of the faces. And this is a way to kind of think about that and visualize that. Now, if I were to roll a die 10 times, and let's say on those 10 rolls, I only do 10 rolls, and all 10 of them turn up 1. Right? If I roll a die 10 times and I get 1 10 times, what should I think? Is that likely to happen? Right? Is this likely? No, right? Even without knowing fundamentally, this kind of information, of knowing the quote-unquote distribution of die rolls, if I were to roll a die 10 times in a row, you should try it. Just try to roll a die and get 10 ones in a row and see how often it happens. Maybe do it 20 times. Attempt it. See if you even get it once. If I were to actually roll a die 10 times and get 10 ones in a row, I should definitely suspect that my die is not a fair die, right? It's not impossible to get 10 ones in a row. It's not impossible, but it is extremely unlikely, right? It's not impossible, but it is extremely unlikely. How unlikely is it? Well, what we'll see, and we won't talk about how this is calculated, but what we'll see is that I should expect to get a 1 10 times in a row, approximately 1 in 60,466,176 rolls. Okay, attempts. I shouldn't say rolls, I should say attempts. Right, so I'm going to try quick. I roll it once, I roll it twice. Okay, I failed. That's an attempt. So if I do that 60,466,176 times, I should expect to get a string of 10 ones once, approximately. Right? So a die roller would have an intuitive sense of the relative frequency of ones in a roll, even if he doesn't have a rigorous understanding of the theory of probability. Right? And a die roller would know that this is extremely unlikely. And if this happens, you should definitely suspect that your dice is loaded. Okay, and so just an introduction to probability. Now, this is another example, obviously, of sort of having a relative frequency or an empirical sense for how likely something is. What we seek in this opening 10 lectures is a rigorous theory of probability. So we need a rigorous theory of probability that agrees 100% with this mini trials approach, this empirical approach, right? And so that's what we're going to be focused on in the next couple of lectures. Right, we all have this intuitive sense of doing things many, many times and having a certain frequency of outcomes. What we need to do is what we want to do is understand in a rigorous way how that works mathematically. Right, and so that'll be the first big topic that we need to cover. And really, what all that amounts to is we're going to define probability rigorously and we're going to build it up. Okay, and our goal is to have that rigorous theory of probability agree 100% with this mini trials or empirical approach. Okay. All right. So I said that would be conversational. It's a pretty conversational section. The next section from here on out will be more mathematically rigorous. Following this lecture, we're going to do just a quick review of set theory, notation in particular, some of the basics, just to make sure that it's top of mind, because our definition of probability is going to rely heavily on set theory and the associated notation. So until then, take care.